All right, so we're trying to match each graph to its equation, or each equation to its graph. So there are a couple things we can use that we learned about polynomials last class. So we can use the end behavior, right? Because the end behavior of the graph tells me about the leading term of my formula, right? So remember, even degree means either both arms are up or both arms are down. And the leading coefficient, positive means arms up, negative means arms down. And then an odd degree means one arm up, one arm down. And the leading coefficient positive means right arm up. Leading coefficient negative means left arm up. So let's look at this first graph. Both arms down, right? So is it even or odd degree? Even degree. Positive or negative leading coefficient? Negative. So let me just jot this down. Even degree. And the degree, remember, is the highest power on x. And then negative leading coefficient. Just write LC for leading coefficient. So let's see, which of my formulas has an even degree with a negative leading coefficient? Five. It's the only one. 5. The degree is 4 and the leading coefficient is -1, right? That's the highest power on x. So its degree is 4. The number in front of that x to the 4th is a -1. And that's the only one that has even degree with negative leading coefficient. So this one's got to be 5. Okay. All right, and then we can just do one last thing to sort of verify that we're right. We can look at the number of extrema. So we've got 1, 2, 3 extrema, which means that my degree has to be at least 4, right? Because when you have the number of extrema is the most it can be is 1 less than the degree. So if I have 3 extrema, I'd have to have at least a 4th degree polynomial. Okay, so that agrees with 5. And then let's look at one more thing. How many x-intercepts we have? 1, 2, and how many are right here? 2, yeah. It only touches once, but when you have this bounce off effect, remember when it bounces off the axis, that indicates an even multiplicity. So we have 1 here and 1 here. There's 1 here, but it has multiplicity 2, right? So we have 4 x-intercepts, which means we have to have at least a degree 4 polynomial. So that also agrees with choice 5. All right, how many x-intercepts does this graph have? 3. And how many extrema? 2. So what degree polynomial am I looking for? At least 3. Okay, good. At least 3. And then looking at the end behavior, we know that we have one arm up, one arm down, so it's going to be an odd degree. And since the right arm is up, my leading coefficient is positive. Okay, so I need to find a 3rd degree polynomial with a positive leading coefficient. What do you think? 3. Yeah, 3 is the only one. X cubed cubic polynomial, positive leading coefficient. And that's the only one. Okay, looking at C, this also looks like a cubic because it's got 3 zeros and 2 extrema. But the left arm is up, right? So I'm looking for a cubic, but with a negative leading coefficient. So that would be 2. All right, D. That's a parabola. So it looks like a quadratic function. Both arms are up. Both arms are up, which means positive leading coefficient. So that's got to be 1 or Just one, yeah. Sorry, I was looking at 5, but it's written out of order. Yeah, so 5 is actually a 4th degree. Okay, so it's got to be just 1. Good. All right, now E has 1, 2, 3, 4, 5 x-intercepts. If you count the bounce off as multiplicity 2, which we do, right? It's got 5 x-intercepts and 4 extrema, right? The extrema are 1, 2, 3, 4. So I'm looking for at least degree 5. So I'm looking for degree 5, and the right arm is up, which means positive leading coefficient. Degree 5, positive leading coefficient, 6. All right, and then F, what degree does F look like? 4, yeah. It's got 3 extrema, and it has 1, 2, 3, 4 x-intercepts, because you count that bounce off as a double. So I'm looking for a 4th degree leading coefficient, positive or negative? Positive, because both arms are up. So 4th degree positive leading coefficient would have to be 4. Good. Okay, if you were to use a polynomial to model the population size of a growing city over time, would you use a positive or negative leading coefficient? Positive, right? Because if it's growing over time, you want the end behavior to the right to go up, right? So whether you use an even or odd degree polynomial, we don't care what happens on the left. We just want to make sure it grows when we go to the right as time goes forward. So we would use a positive leading coefficient. Okay, so look at this scatter plot. What degree polynomial would you choose to model this data? 4, how come, Cassandra? Yeah, there looks like there's 3 extrema, like this. If you were to sort of connect the dots like best you can, right? We've got 1, 2, 3 extrema, which means my degree has to be at least 4, right? I could choose any even degree, right? Because of the both arms up thing, I definitely want to choose an even degree. And it needs to be at least 4. So I could choose 4 or 6 or 8. But typically when you're choosing a model, you choose the simplest one possible that will capture the data. So we would choose the lowest possible degree of 4. Yeah, yeah. Yeah, you can definitely model that with a 6th degree. You can create a 6th degree polynomial with only 3 extrema. Yeah. All right, so today we're going to talk about polynomial regression. Before we get into this, let me just pull up our schedule so you can see what I changed based on the fact that I wasn't here Friday. So the Friday's class was canceled. I just moved everything down a day. So what we're doing today is what was scheduled for Friday. And then everything else is the same up until here, right? We were supposed to have quiz 6 in class, so it's going to be a take home. Right? So that saves us yeah, so now there's no class 36. Class 36 was supposed to be the quiz. So that's what we're doing. Everything's just pushed down a day until we get to that quiz and it's a take home. But some of your due dates have changed. Right, quiz 5 is pushed back a day, so it's due a day later, and project 3 is going to be due a day later. Anybody not have project 3, by the way? Okay, so earlier this semester, we entered some data into our calculators or into GeoGebra and performed linear regression. So the day we did lines, there was one problem. Some of you skipped it, but we're going to enter some more data into calculators today and come up with models for data that does not fall on a line, right? If it doesn't fall on a line, we can use a polynomial model instead of a linear model. So before I get into all the hows and what buttons to press, right, I just want to preface all of this that today is an exploration to see what your calculator can do, think about what kinds of models are appropriate for different types, for different data sets. But knowing exactly how to do this on your calculator or in GeoGebra is not going to be tested, right? So this is an exploration to play around with the technology, but you're not going to be tested on the use of the technology. Okay, just want you to see what it's capable of. So something that I might put on a test might be something like this preview exercise. I might give you a scatter plot and say, what degree would you choose to model this? Or I might give you a model. I might give you some data and say, a good fit for this data is this 4th degree polynomial. Use it to make some predictions, something like that. Okay, so we're going to do an example. Let me hand out some graphing calculators in case you all want to. Okay, so everybody's got a graphing calculator. We're going to put this data into the calculator. So I'm going to let T be the number of years since 1970. So 1970 is actually going to be year 0. So what's 1975 going to be? 5. Good. All right, so to enter it, you press the stat button, because this is a statistics thing. We're dealing with data. This is statistics, right? So you press the stat button and choose option 1, edit. We want to edit our lists. You got list 1, list 2, list 3 across the top. If you're missing a list, if it just starts with list 2, that's okay. You can use list 2 and list 3. It's no big deal. If you have some data in there already, you want to get rid of it. The way you get rid of it is you highlight the name of the list. Put the cursor on the name of the list. Press clear. Don't press delete. Press clear. It looks like nothing happens, but when you move the cursor back down into the list, it all goes away. So do that for any lists that have data in it already. The next step is to enter all of your X data in list 1 and your Y data in list 2. So my X data, I'm putting in years since 1970. So my first data point's at 5, and then 10, 15, 20, 25, and 30. So that's my X data for year. And then my Y data is the number of women in the full-time civilian labor force with children under the age of 6. So I'm going to put those numbers next to the corresponding year in list 2. So 4.851, 5.886, 7.322, 8.732, 9.587, 9.736. Okay, it's super easy to make a typo when you're entering data, but one quick thing you can do to check that you didn't make a mistake is that your 2 lists have to be the same length, right? So it's just one quick, check that before you move on. Make sure you haven't skipped a number somewhere. All right, so my question is now asking me to find the line of best fit and the parabola of best fit. Okay, so I'm going to go through all the commands on how to do this, but there's a step-by-step instruction sheet called How to Perform Polynomial Regression, like on the next page. So when you try to do this on your own, it is all written down. You don't have to frantically take notes on what buttons to push. Okay. All right, so I want to find the line of best fit and the parabola of best fit. So I'm going to quit from here. Anybody need help entering their data before we move on? So to quit, you press second, quit. Right next to second is a quit button. Yeah. So you're back in your home screen. All right, so now I want to do some statistical analysis of my data, right? So I go into my stat button again, but this time I want to do some calculations. I want it to calculate the line of best fit and the parabola of best fit. So I cursor over to the calculate menu, and I have options 4 and 5 are linreg for linear regression and quadreg for quadratic regression. Okay, so we'll do the line first. So you choose option 4, linreg. Now, if you have an older calculator, this is all that pops up, right? And you have to type in where your data is. You have to tell it my data is in list 1 and list 2, and where to store the result. Okay. If you have a newer calculator, it prompts you for that information. There's a little line that says X list, and you type in list 1 next to that. Okay. So I'm going to type in list 1. That's second, the number 1, gives you list 1, comma, list 2, second, the number 2. So again, if you have a newer calculator, you're prompted for that. Right next to those lines, just write list 1 and list 2, where it says X data and Y data. Then the last thing you have to put in is where to store the regression equation. I'd like it to store it in Y1, okay, so that when I press graph, it'll automatically graph. So I want to put a Y1 there. This is kind of a pain. It's the vars button, vars for variables. Okay. Go over to Y variables because I want to put it in Y1. Choose option 1, function, because Y is going to be a function. And then you have the list of all the Y's. So choose option 1 for Y1. If you have an older calculator, you just press enter. If you have a newer one, you highlight the word calculate and press enter. Okay. All right, so I've got my line of best fit here. It is Y equals, I'm just going to round a little bit here, 0.21x plus 3.99. And my R squared value is 0.96 if I round to 2 decimal places. Anybody not have R and R squared? Just one person? Okay, I'll come fix it. Okay, I think we're all on the same page with the linear regression. Okay, so now to get the quadratic regression, which is a parabola of best fit, I'm going to go back into stat, go over to calculate, and this time choose quadreg, right? Quadratic functions look like parabolas, so I choose quadreg, and again, I have to type list 1, comma, list 2, comma, Y1. Actually, I'm going to choose Y2 this time because I want to have both of the equations stored. Okay. Now, some of you may have your data in lists other than list 1 and list 2, like if list 1 were deleted and you were using list 2 and list 3. In that case, in your command, you want to have list 2, list 3, Y2. Okay. So I hit enter, and it says that my quadratic regression is Y equals 0.005 x squared plus 0.38x plus 2.87. Okay. And my R squared value is 0.99 if I round to 2 decimal places. So let's look at a picture of the data with my 2 models and see how good it is. Okay. So I have to pick a good window to make sure I can see all of the data. So my data goes from 0 to 30 for X, right? Because I started 1970 with 0. So let's go 0 to, say, 35, just so we can see a little bit past our last data point. And then Y starts at 4.8 and ends at 9.7. So let's go like 0 to 12, just so you can see a little bit before and a little bit after the data. You leave the scale at 1. I almost never change the scale. Doesn't make much of a difference at all in what your graph looks like. So I just always leave it at 1. All right, press Y equals. So it looks like there's a bunch of messy stuff in there. Y1 is your linear regression and Y2 is your quadratic regression. I stored them there so that I wouldn't have to retype them, right? And then you also want to make sure you turn on plot 1 in the upper left because that's your data. So you highlight plot 1 and press enter, so now it's highlighted permanently. You don't have a Y2? What? Let me see. You must not have stored it.
Really?
Yeah, you just did quad reg and you didn't type in the rest of the commands. You got to do L1, comma L2, vars, y vars, function y2. And now when you go there, there it is. Yep. All right, so once you have your window set and y1 and y2 and plot 1 all have things in them, press graph. So you can see your data. The first line that graphs is your linear, and then the curve is your quadratic regression. Your data is not there? Okay, which model looks better, the line or the parabola? The parabola definitely looks like it comes closer to all my data points, and the R squared value supports that it's a better fit because it's 0.99 as opposed to 0.96, closer to 1 means better fit. Yep. Okay, so now I've got 2 different models. I want to use both of them to predict the number of women who are working with children below the age of 6 in 2011. Okay, and then we want to think about how much we believe in this prediction. Okay. So 2011, how many years after 1970 is that? (1970 to 2011). (41). Thank you. 41. Okay. All right, so quit from your graph. Just hit second quit. If there's anything in your home screen, you can just clear it. Okay. I'm going to use my table to help me answer this question. So table is a second function over graph. So you hit second graph and you get a table. And you can either scroll to 41, right? If you have a scrolly kind of X table, or it might be set where you can just type in the value you want. So I can just type in 41 for X, and it will tell me Y1 and Y2. So my linear model was stored in Y1. So when I type in 41 for X, it tells me that Y1 is 12.646. That's my linear model. And Y2 is 10.33. Okay. That's my quadratic model. It's stored in Y2. So it's basically, I just plugged in 41 into these 2 models, but I let my calculator do all the computation. Okay. Okay, how do you feel about these 2 predictions? They're pretty different because these are millions of women, right? This is in millions, yeah. Millions of women predicted to be in the workforce. Women with children under the age of 6. So it's like 12.5 versus 10-ish. So it's a big difference. Which one do you feel more confident in? The parabola, how come? Okay, that's some reasoning. Yep. So you think that's going to peak, that the number of women in the workforce will peak and then come back down? That's what parabolas do, yeah. So you have to sort of ask yourself, do you think that's what's going to happen with the number of women in the workforce? Is it going to peak and come back down? Is it going to keep going up forever? It's not a percentage, it's just number of women in the workforce. So it's compared to nothing. It's just the number of women working because population is growing. Yeah. So I think that it makes more sense that for the linear models, end behavior makes more sense. Even though it's not quite as good of a fit, that its end behavior works better. So, and since 2011 is pretty far outside my data set, I'm going to go with the linear model because I believe in its end behavior. Okay. So I'm not going to pick a percentage for my confidence level. I'm just going to say better, right? Better end behavior. Better end behavior for the linear model, but the parabolic model fits really well the data that I have. So if I want to do some interpolation, right, if I wanted to predict 1982, right, which is in between the given data I have, I would use the parabola. So this is better for interpolation. Yeah, and this one is end behavior. We could also say this is better for extrapolation. Okay, that's when you're making predictions outside of the data set. So the R-squared value is not the end all and be all of which model is the best, right? It's one little piece of information. You also really need to think about the end behavior and what you think the end behavior is going to do. Okay, so oh yes, we just talked about this, what the end behavior for each of these two models are. So the linear model is going to go up forever to the right, but the quadratic model is going to come back around, right? So my linear model is going to have end behavior that looks like that, goes up forever. Quadratic is going to have end behavior that goes like that. So linear, this is going to be better for modeling future numbers. Okay. Right, because the quadratic is eventually going to predict negative women in the workforce, which doesn't even make any sense. Okay, so here's some sort of step-by-step guidance on how to do modeling, right? First, create a scatter plot of your data. Use your calculator to just look at the data, or you can just sketch it on a piece of graph paper. Decide whether you think it looks like a line or a parabola, or a more curvy polynomial would be a good fit. Okay. The more peaks and valleys your data has, the higher the degree has to be. Find an equation for your model. Your calculator does that part. Okay. Verify that your equation has a graph that comes close to the points in the scatter plot, right? So look at your scatter plot and the graph of your model. Make sure they look close. If they're not, make sure you didn't make any typos. And then also, if you didn't make any typos, you might say, oh, I chose a bad model, right? Start again. Then you can use your equation to draw conclusions, make estimates, make predictions. So for selecting a model, you have to decide what degree polynomial to use. Your calculator can do linear, quadratic, cubic, and quartic regression. Okay, so that's up to 4th degree. Some criteria for selecting a model. The graph should fit the points reasonably well. Use the simplest model that captures the pattern of the data, right? So if you have 3 extrema, you want to use a 4th degree, not a 6th degree, right? Use the lowest degree you can to capture the data. And the model should make sense within the context of the real world situation, right? So just like with the women in the workforce example we just did, the end behavior should make sense with what's really happening in the real world. All right, so I have some data for you guys to do and use your graphing calculator on. Again, if you forget the steps with the buttons, page 19 has step-by-step how to do the regression on your TI.